Okay, welcome everybody. Settle down. Come on, take a seat.
Is that for your? When I get something?
Katya's here. Welcome, Katya.
Okay.
And today we have Banafshe. Banafshe is really a PhD student. But she's been working on robots and state construction and knowledge, empirical knowledge sequences for some time. And so today she's going to talk to us about a trace-conditional testbed. So thank you. Welcome.
Hi. As Rich said, I'm going to talk about a trace-conditioning testbed. I should mention that a group of people have been working on this testbed, Amir, Brian, Adam, Rich, and myself. Today I will talk about the experiments that I've done using this testbed. So there seems to be 3 challenges when it comes to constructing the state. So first thing is like how to build a representation which is suitable for learning. Second thing is that how to learn when our observations do not carry enough information. And the second thing is how to learn complex like nonlinear functions in linear representation systems. So we like linear systems because they are efficient in terms of computation and data, but they do not account for the intersection of features. So if a feature is only useful if another feature should have a certain value, linear systems need to be provided with that information. So the part of the agent that construct the state is called the state update. This picture here is from the book. You all might have seen the agent environment interaction loop, where we have the agent and environment interacting. The agent performs an action and the environment provides the state. A more general case would be when the environment only provides observations and not the state. So the agent is responsible for constructing the state. So here, the board only provides observations, and this box with U in it is the state update function, which given state, action, and observations provides the next state. So in this talk, I will explore constructing the state using a simple problem. The problem is a trace conditioning testbed. The testbed consists of a series of trials. At each trial, a sequence of stimuli is presented. A US, or unconditioned stimulus, which is what we are interested in predicting, and a CS, or conditioned stimulus, which is it provides some information about the US. And here you can see that CS happens, and after some time US happens, and there is this interval between the CS and US. The length of the interval is called ISI, for interstimulus interval, and in this case it's 10. And if you are familiar with classical conditioning, you might heard of Pavlov's dog, where the dog is presented with food, but before presenting the food, we always have this ringing of the bell. So after a while, the dog understands that there is a relation between like presenting the food and ringing of the bell. So in this case, food is a CS and bell ringing is US, and what we actually want to predict is the food, which is US. So the testbed also includes 10 distractor stimuli that happen in a Poisson fashion. And here I'm showing the full trial. In the previous slide, I showed the most interesting part of the trial. Here I'm showing all the trial. And so after US happens, there is this inter-trial interval, which is the time till the next CS happens. And that is uniformly distributed between 90 and 110. And as I said, we have 10 distractors. You can see the distractors. They have a decreasing frequency, meaning that the first distractor happens more often, and the next happens less often, and the last one is like the least often. Yep.
In the previous slide, can I think of this long period of time as like the lead up until the next time we see the CS?
Yes, yes. So here, the next CS is happening.
Is the least common distractor more common than the CS, or is it less common than the CS?
I think it's as common, but I don't exactly remember. I think it's as common.
Well, you know, it's 1 out of 100 time steps. Be the distractor.
Yeah, and the length of trial is about,
About 100.
yeah, so I think it's about the same. Okay, so what we want to predict is the expected discounted sum of the US. And so we're using discount factor 0.9. So I'm showing the return here, and we want our prediction to look like return. Like as we approach the US, the predictions become higher. Okay, so the question is, why is this even challenging? So this is a simple problem, but yet it's challenging because we have this interval, which is empty, and during which nothing happens between the CS and the US. And this interval is called the trace interval. And the agent needs to keep some kind of a trace of the CS to be able to predict about the US, and or like fill this gap. Just note that a trace of the CS is not the same as eligibility traces. It's a different thing.
But the distractors do happen in this interval, right?
Yes, but the thing is that distractors are not providing any useful information for predicting the CS, the US. So, okay, so let's look at a simple solution method. We can use TD lambda with lambda 0.9, and for feature representation, we can use a presence representation, which is basically having one feature per stimuli. So we have a CS, a US, and 10 distractors. We have one feature per stimuli. We also have this bias feature. So here is the result for the presence representation after 2,000 trials. I'm showing a CS, US return and the prediction. You can see that the prediction, so we like prediction to look like the return, and it's not really satisfying. There's only one thing happening here at time of CS and one thing happening here at the time of US. And so here I'm showing the representation to give some reasons why this is happening. This is the bias term, which is always on. This is CS, which is only one when CS is on, and this is US, which is one only when US is on. So during this time, feature representation is just one, and maybe some of the distractors are on too. And note again that we did use eligibility traces. So eligibility traces do not help us to fill the gap. It just helps to understand that there is some relationship between the CS and US, and like that's why this thing is happening, but it's not enough.
So the return, you sometimes will call the ideal prediction. We'd like our prediction to look like the return, and it doesn't look like it so far.
Yeah.
So that's not good.
Yeah.
Okay.
Okay, so a possible solution is to use traces of stimuli in representation. So we have these 12 signals, CS, US, and the distractors, and we can compute a trace of each of these signals, and using a trace parameter like 0.9. And we can also tile code the trace, and then our representation would look like this. Again, we have one feature per stimuli, but we also have tile coding of the traces of each of the signals. So here is the result for the new representation. It's again after 2,000 trials. You can see that the prediction is much more like return here, and that's good. So I've been talking about like the CS, US, and distractors, and what we like our algorithm to do is to learn which feature, like associate higher weights with features that are useful, and associate lower weights with features that are not useful. So here what I'm showing is sum of absolute weights of features associated with traces of each of these stimuli over trials. And you can see that the algorithm associated higher weights to CS and US compared to distractors, which is more like a sanity check. A question is, what happens for higher values of ISI? So as you may remember, the time between onset of the CS and onset of the US is called ISI. And one question is, what happens if we have like longer ISIs? Because, yeah.
Did you tell us what ISI stands for?
I did.
Okay.
But maybe we can use a reminder?
Yeah. So interstimuli interval. Yeah.
How come the green shape doesn't look exactly like the black one?
Okay. It's because so this is where CS happens, and before this there is really no information which is useful. So before here there is not really much that we can do.
Question: why is the ideal prediction not exactly like US? It's because the uncertainty of US. So the ideal prediction you wanted to actually predict US, but it's actually like this.
I understand. It's a good question. What I want the ideal prediction to be is sum of discounted like of the US. So I want the prediction to increase as we get closer to the US. An alternative is that we do something like only have this guy here. That's what you're saying, right?
The ISI was always 10?
Before this slide, yes. Yeah, I use a fixed ISI. I didn't use variable ISI.
What even like sum of discounted US, because so there's one US that like appears as
So US is at each time step we have a US, right? It can be 0 or 1. You can think of it as reward.
rewards it for the future and then okay now.
Yeah, okay. So we want to know what happens if, because we yeah.
So when you're saying that is the ideal prediction, does it really make sense to have something beyond?
Yeah, it's a really good question. Probably not, because so there is this ideal prediction.
You have to finish the sentence. You understood, I didn't understand.
Should there be some kind of prediction, non-zero prediction before the CS?
Before. Ideally there would be, yeah.
Before the CS?
Yeah. That would be better. Wouldn't it be better?
But how?
Yeah, but we don't expect.
Just because something is impossible doesn't mean it's not ideal. I think it's fair to call that ideal. Besides, in a variation of this, there might be more stimuli with different predictiveness, and you might be able to get better, closer to the ideal. It's just a word anyway.
Okay. So we want our algorithm to be robust to this ISI. So if ISI is longer, we want our algorithm to still work. So what I want to do is to change ISI and see how the performance changes. For performance measure, I use root squared return error at CS onset. So you can see that this is a whole trial. We want to reduce it to a number. So what I'm doing is just compare the, compute the difference between prediction and return at the time of onset of the CS. But you could use different things, like you could compute the average or compute return error at the time of US onset. So here I'm showing RSRE for the final trial over different values of ISI. You should notice that I'm adjusting the trace parameter with ISI. So if ISI is bigger, I'm using bigger trace parameters. So for example, if it's 10, I use 0.9. If it's 100, I use 0.99, and so on. And it seems like, here I'm using the same algorithm, the same parameters, like the same lambda tile coding parameters, and it seems like the performance is robust. Yeah?
Can you tell us a little bit about how you calculate these?
Oh, okay. I used 2 tiling with 16 tiles for each trace.
Tilings are capturing the interaction between features, right?
Interaction between features? No, I'm tile coding separately.
So you are not capturing interaction
No.
in any.
Okay, so how successful was tile coding the traces? There are 3 levels of success to this problem. The first thing is that whether we were able to represent the answer, and it seems like we were able to represent the answer. The second thing is that whether we could find the answer efficiently, and we did not address that in this talk. To answer that question, we need to compare the algorithm with natural competitors like LSTMs and GRUs. And the second level of success is that the algorithm, like the agent itself, discovers the useful features. For my experiments, I handcrafted the features for the agent, but eventually we want to do the discovery. Take-home messages. The problem of representation learning, partial observability, and learning nonlinear functions all involve the state update function. And the trace conditioning testbed is useful for investigating the state update function. And tile coding the traces is a natural way for enhancing the representation for this task. And we, for future work, we need to investigate the efficiency of the method and address the discovery problem. That's it.
Can you talk a little bit more about what you mean by efficiency in this case?
I mean, so it takes it a while to, you can think of having learning curves of how soon the error decreases. So how soon it learns the prediction. That's what I mean by efficiency.
How many trials did it take to learn that pretty good approximation to the
I'm-
ideal prediction?
I'm showing for 2000s, but I'm not sure at which trial it learned a good approximation.
CS appears randomly during the trial, right? And then
No. So
its position is fixed.
yeah, its position is fixed. It's the start of the trial. Yes.
It's hard to tell from the graph, but is the prediction, does it exactly correspond to the return, or is there some small difference?
There is some small differences.
But they can be random, right? They don't
Yeah. You're suggesting that instead of having a fixed, ISI.
Not ISI.
Okay.
When CS occurs, that point is that fixed or is that random?
In this case, it's fixed.
But it can be random, right?
Yeah, it can. Yeah, it
So
can be
usually
random.
It doesn't assume that it has to be fixed. It's just that after CS, 10 seconds after CS or 10 units of time, US would appear.
Yeah, but do you think there is any point to having onset of CS random? Because I think that the relation between
Because
CS
yeah.
and US is
You had
important.
another plot which showed that the weights on distractors are very small. If you hadn't showed me that, I would have assumed that maybe it is representing US with some other, by exploiting the noise in some specific way.
Mhm.
But yeah, you did show that plot, so maybe not.
Yeah.
Can you go to your plot of the multiple
ISIs?
ISIs?
I think so. Okay.
Right. So there's a lot going on here. Maybe you'd like to unpack it a little bit.
Okay.
When you say the root squared return error,
Mhm.
is it the average over all the time steps, or is it the mean root squared, or
It
is it the
is.
sum? Is
It is at the time of. I'm looking at the final trial, and then I'm looking at the difference between return and prediction at the time of the onset of CS. Yeah, you could do like average over like this time, or like the whole thing, or like any points, but
Okay, so just at that one moment.
Yeah.
And then when you show the comparisons with different ISIs,
mhm.
these are in some sense different RL questions, right? Like they're with different timescales.
Yes.
So should the ideal answer be exactly the same for all of them, or
Okay,
like?
you're saying, does it make sense to even make this comparison, right?
Yeah, I guess, are we trying to compare them at these different points, or, yeah, are we comparing 2 to 10 and saying it's more or less accurate, or are we comparing it to some thing which is not shown, which would be maybe a bad predictor or a
Mhm.
good predictor? Like, how should we read this graph?
Okay. I think what I was thinking about was that it seems like so adjusting the trace parameter is enough to get a good enough performance, but I understand that maybe making this comparison does not make sense.
Maybe it does. Like, would the
Because like the scale of the prediction might be different when we change ISI. Yeah.
Before you go on to consider the next two things, the speed and the discovery,
Mhm.
you might want to do another one like this that's a little bit more sophisticated. That is, if you do two kinds of trials,
Mhm.
one where it's at 10 time steps, ISI, and one that's 20 time step ISI. And you like mix them together, like half the time it's one, half the time it's the other. And then you should find that the prediction is high. You should see like 2 peaks. I think. Yeah, half the time you get one, half the time you get other. And you should.
So here, you're saying about the prediction, right?
Yeah, so like the prediction should go up like that, and then when if US doesn't come, it should fall down and then
go up again.
So you would see a more sophisticated, so it would represent the expectation of the return. It will be one, it will be either like this way, or it'll be the same thing but 10 steps later. And so I think it'd be good to do that.
Sorry.
When you were talking about your evaluation metric, which was like looking at when the CS happens and how closely the prediction, that's kind of testing when the prediction is made, sort of how correct, or when the stimulus is about to happen, how close is the prediction. But it's also, like it should also be testing the opposite case, right? Like when the stimulus doesn't happen and prediction should be low. Because in principle, an algorithm could just predict a constant. And
Yeah. Like something, like maybe like event testing here is important because like we don't want the predictions to be high there.
Right, like
That's
you think
what.
of it as a machine learning problem. You're taking a history and you're predicting whether the event's going to happen or not.
Yeah.
And you want not only positive examples, but also negative examples.
Yeah.
Right?
At the beginning, I was looking at the average, but the problem is that with like higher ISIs, it would be in favor of the cases with higher ISIs because there will be a lot of like zeros.
Right, you have to choose how many
Yeah.
positive examples versus negative examples you have.
Yes. Do you have any suggestions?
I think it's like I think you have to think more about exactly what your performance metric has to be, and that should give rise to sort of a natural performance criteria.
Okay, Matt.
So 2 easy questions. Thanks for talking. This is good. So for the slide after this, where you're comparing the different time steps, do you know what the RSRE would be for like the 0 prediction? So if you were just predict 0 on set, what
That's a
would that
good
be?
question.
Because it's gamma to the 1,000 is your return. That's a really small number. And then another question is for your feature traces, were you doing accumulating or replacing traces?
Accumulating. No, sorry, replacing traces.
Okay.
Yeah.
I was thinking about a broader question of a little bit going back to the question of whether this is the ideal prediction target. So in a way, what you're trying to do is you're trying to predict when the unconditioned, or what's US?
Unconditioned.
Unconditioned
Yeah.
stimulus occurs, given when the conditioning stimulus occurred, right? Like it's like the length of the interval that matters, and you can encode that in many different ways. This is one encoding. You can imagine many other things. Have you tried to think about whether these decisions of like which way to represent the information that is the uncertain information that is there is going to lead to an easier or harder prediction problem? Maybe you're setting like, I know that the brain is doing something like this, or I suspect that it is, that will be the claim, but is that a good thing?
So you're saying that maybe if we rethink the ideal prediction, maybe the whole task would be...
The underlying mathematical problem is just to predict when the next event is going to happen, condition on the previous event. And maybe the brain has to do this because it has limited capabilities in various ways, the little elements that it has to build everything from is a limited set. We don't have those restrictions. So does it make sense to study this problem?
Okay.
from a computer
see.
science perspective, right? Like, or information theory perspective.
I see. But still, so maybe the main problem is that there is this interval where nothing happens. So we're gonna need some kind of a memory or something.
Sure. As
Okay.
you said, LSTM, blah, 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 there are zillions of solution techniques out there. And not all of them, like if you force LSTM to create a prediction signal like that, then maybe it's going to have a hard time. But if you change the representation with which it represents this time information that you're trying to encode, maybe it's going to work better. Right?
I see.
So it's not. I mean, this is a valid problem for sure. Not questioning that. I'm just wondering about whether, you know, maybe the bigger question also makes sense.
Yeah. Yeah, I see. But yeah, I haven't thought about that. Yeah, thanks.
Okay, thank you, everybody.